Welcome to the deep dive. Today, we're going to really get into something fundamental. It's the physics that underpins pretty much everything digital you interact with.
Yeah, the physics of computation itself.
Exactly. We're not talking code today, not software, but the real nuts and bolts, or maybe more like the electrons and the energy that, make computers tick, what limits them, and maybe where they're headed.
And we've got a great guide for this, Richard Feynman. We're diving into his lectures on computation. It's a fascinating look at how physics fundamentally shapes computing, right? From, well, simple logic gates up to the really big theoretical questions and even quantum machines.
What I love about Feynman's approach is how it just forces you to remember computers aren't these abstract math things floating in space. They're physical. They're built using the laws of nature.
Absolutely.
So our mission today is really to pull out the most important nuggets from these lectures, the insights that help explain why computers work the way they do, why they have speed limits, why they, get hot.
And it's a surprising mix, isn't it? You get these deep questions like, what can we even compute in principle? And then, boom, you're right back down to the nitty-gritty of tiny electrical switches and how much energy it takes to flip one.
Yeah, it reveals these fundamental limits you might just never have considered otherwise.
Definitely.
Okay, so let's jump in. Feynman starts with this core idea. Computers are physical systems. They're built from simple bits. He kind of strips away the magic.
Yeah, he talks about it like building a house you need bricks, mortar, wood, sweat. Or for a machine, maybe control valves, or even simpler, like beads on an abacus. Fundamentally, he says it's like shuffling bits of paper around.
Which in our modern world means shuffling digital signals,
Yeah.
right? The ones and zeros.
Exactly. Physically represented by voltages or electron spins or, well, whatever physical medium we choose.
And to make this really concrete, he uses this great analogy. Imagine a whole bureaucracy of file clerks. That's your computer, a physical system doing calculations.
Right. And these clerks, they only do incredibly simple things like grab a specific card, maybe take card X and put it in a temporary spot.
Or check what's on a card. Is this card marked California? And they use these little temporary storage areas.
Ah, yes, the temporary spots. Those are crucial. They're basically the registers in a real CPU, little holding pens for data, labeled ABX.
And there's a special one too, right? The C register.
Yeah, C register. It's just a single bit, but it's vital for arithmetic. It holds the carry bit, just like when you do addition by hand and you have to carry the 1.
So any big, complex task calculating pi, editing your vacation video, whatever, the computer breaks it down into just a huge, long sequence of these dead simple instructions.
Then it just chugs through them, one after another, guided by something called the program counter, or PC.
The PC just points to which instruction to do next.
Pretty much. It holds the memory address of the current instruction. Once that's done, the PC just increments. So PC becomes PC plus 1. It points to the very next instruction. That's the core fetch-execute cycle. It's how most computers, compute.
Okay, but how do we physically make something do those instructions? That's where the electronics come in.
That's where logic gates come in. They're the physical electronic realization of these basic logical steps. Feynman really focuses on the fundamental trio, ANY, OR, and NOT.
Right, the building blocks.
And you can describe them really simply with truth tables. An AND gate only outputs a 1, or true, if both of its inputs are 1.
And OR is if either input is 1.
Exactly. And NOT just flips it. A 1 becomes a 0, 0 becomes 1. Simple inversion.
Now, here's something Feynman really stresses, and it's a powerful physical idea.
Ah.
AND, OR, and NOT together are complete.
What does that mean, complete?
It means you can physically construct any possible logic function, no matter how complicated, just by wiring together combinations of those 3 basic gates. That's it.
It's pretty amazing. He also talks about XOR, the exclusive OR gate. That's useful. In addition, it gives you the sum bit, while an AND gate gives you the carry bit we mentioned.
But even XOR, you don't need it fundamentally, right?
Correct. You could build an XOR gate using just ANDs and not Ts. It just reinforces that core idea. Complex logic from simple physical pieces.
Okay, but just processing inputs isn't enough. Computers need to remember things, sequence operations correctly. How does that work physically?
Right. You need memory and timing. So that brings in sequential logic. You have elements like the RS flip-flop, which can physically store a single bit of information. It remembers.
But timing's tricky, isn't it? Signals don't travel instantly.
Exactly the problem. Signals take a finite time to propagate through wires and gates. If inputs to a gate arrive at slightly different times or change too quickly, you can get glitches, uncertainty, the whole thing can become unstable.
So you need like a conductor.
Yeah.
An orchestra leader.
That's a great way to put it. That's the role of the clock signal. It sends out regular pulses, like a metronome. And these pulses tell all the components, okay, input should be stable now, process them. It synchronizes everything, making sure operations happen in the right order and reliably.
Got it. So we have physical components, basic logic, memory, timing. That seems like the practical side. But Feynman then takes this interesting detour into the theory, right? The absolute limits.
He does. He goes back to the 1930s when logicians were asking these really deep questions. What does it even mean to compute something? What can be computed, even in principle?
This was around the time of Gödel's work.
Precisely. Gödel has shown that even basic arithmetic had inherent limitations, things that were true but couldn't be proven within the system. So people started wondering, are there limits to calculation itself?
And that's where Alan Turing comes in with his famous machine.
The Turing machine. It wasn't a real machine, of course, but a theoretical model, designed to be the absolute simplest thing you could imagine that could still, theoretically, perform any possible computation, anything defined by an effective procedure or algorithm.
So what is it, basically?
Conceptually, think of an infinitely long tape divided into squares. There's a head that can read a symbol on the square it's over, write a new symbol, and move left or right. And the machine itself has a finite number of internal states.
And rules.
Simple rules. Based on its current state and the symbol it reads, the rules tell it what symbol to write, which way to move the tape, and what state to go into next. That's it. It's designed to capture the essence of step-by-step calculation.
And the key difference compared to simpler models, like, say, a finite state machine,
Is the tape. A finite state machine, an FSM, also has states and rules, but its only memory is its current state. You can't remember arbitrarily large amounts of information.
whereas the Turing machine's tape gives it potentially infinite memory.
Exactly. Yeah. The classic example is checking for balanced parentheses, like an F. An FSM can't really do that for an arbitrarily long string because it would need potentially infinite states to count how many opening parentheses it has seen.
But a Turing machine can.
Right. It can use its tape like scratch paper, moving back and forth, marking off pairs, keeping track. That unlimited memory capacity is what makes it theoretically so powerful.
Okay, staying with theory for a moment, he also touches on this idea of countability, different sizes of infinity.
Yeah, it's a bit of a detour, but relevant to limits. He points out that some infinite sets, like all the even numbers or even all the rational numbers, fractions, you can actually list them out. You can match them one-to-one with the counting numbers, 1, 2, 3. They're countable.
But not all infinite sets are like that.
No. The set of real numbers, all the numbers on the number line, including ones with infinite decimal places like pi, is uncountable. You simply cannot make a list that includes all of them.
That's the diagonalization proof, right?
That's the one. No matter how you try to list them, Cantor showed you can always construct a new, real number that's guaranteed not to be on your list. It's a fundamental difference in the size of infinity, and it hints at limits in representation and processing.
So, okay, the Turing machine tells us what's computable in theory, what's effective, but that's not the whole story in the real world.
Not at all.
Yeah.
Because something might be possible to compute, but it might take, the lifetime of the universe to actually do it. This leads to the crucial difference between effective procedures and efficient ones.
Effective means it can be done, eventually. Efficient means it can be done reasonably quickly with reasonable resources.
Exactly. And this is where physics really bites, factoring a huge number into its primes. We have algorithms, so it's effective, but for really big numbers, it's incredibly inefficient on any computer we currently have.
Which is why it's used for encryption.
Right. Breaking the encryption is possible, just not practically feasible. Contrast that with, say, probabilistic primality testing. It doesn't prove a huge number is prime, but it can tell you with extremely high probability if it is, and it does it very efficiently. Practicality matters.
And practicality brings other problems too, like errors. Physical systems aren't perfect. How do computers deal with inevitable glitches?
Yeah, that's a huge practical challenge. The answer is redundancy. You add extra information that isn't strictly part of the data itself, but helps you detect or even correct errors.
Like parity checking.
Parity is the simplest example. You add one extra bit to a block of data, maybe set so the total number of ones is always even. If you receive the block and the parity is wrong, an odd number of ones, something went wrong.
But you don't know what went wrong.
Correct. Parity is error detection. For correction, you need something smarter, like Hamming codes.
Hamming codes. Feynman seemed quite taken with these.
They're ingenious. Instead of one overall parity check, you calculate several parity bits, each covering a different cleverly chosen subset of the original data bits. These subsets overlap.
And the magic is?
The magic is in the pattern of which parity checks fail. If there's a single bit error somewhere in the data, or the parity bits themselves, it will flip the parity of some of the checks, but not others. That specific pattern of failing checks acts like a code, a syndrome, that uniquely identifies exactly which bit flipped.
So you know the location.
Exactly. And if you know which bit is wrong, you just flip it back. Voila, error corrected. It's automatic error correction built into the physical system's logic.
And Feynman tells this great story about how this saved early parallel computing efforts.
Yeah, the gang disk systems. They used many hard drives working in parallel to get speed and capacity. But disks back then weren't perfect. A single bad bit on just one drive could corrupt the whole result. It was a major reliability headache.
So they added extra disks just for Hamming codes.
Essentially, yes. They use redundant disks to store the Hamming parity bits calculated across the data disks. If any single disk had a read error, the Hamming code logic could reconstruct the correct data on the fly, identifying and correcting the error. It made the whole approach viable.
That's clever. He also mentioned using it for debugging.
Right. If the system kept correcting errors that the syndrome always pointed to the same physical bit location on the same physical disk, engineers knew that disk had a permanent flaw and needed replacing. The error correction system doubled as a diagnostic tool.
Okay, so that's handling errors. What about just getting the most out of your physical transmission lines or storage, compressing data?
That brings us into information theory, and specifically Claude Shannon's work. Shannon's limit gives us a theoretical maximum rate for reliable communication over a noisy channel, or a theoretical limit on how much you can compress data without loss.
And it's based on how predictable the data is.
Fundamentally, yes. Information, in Shannon's sense, is related to surprise or uncertainty. If data is highly repetitive or predictable, like, say, the letter U almost always following Q in English, it contains less information per symbol.
And less information means more compressible.
Exactly. Techniques like Huffman coding exploit this directly. You analyze the frequency of symbols, like letters or pixel values, in your data. More frequent symbols get assigned shorter binary codes, less frequent ones get longer codes.
Like Morse code giving E, the most common letter, the shortest code, just a single dot.
Precisely the same principle. It's a variable length code based on probability, achieving compression. Predictive coding is another angle. Predict the next value, encode the difference. And related to all this is the sampling theorem.
Nyquist, Shannon.
Yeah, which tells you the minimum rate you need to sample a continuous physical signal, like audio, to be able to perfectly reconstruct it digitally. It's all about understanding the information content and the physical constraints of representing or transmitting it.
Now, this feels like we're leading up to something really deep. Feynman talks about the ultimate physical limits, connecting computation to thermodynamics.
This is one of the most profound parts, I think, Landauer's principle. Feynman explains that the fundamental, unavoidable energy costing computation isn't necessarily associated with doing the logical operations themselves.
No. What then?
It's associated with erasing information, making logically irreversible steps. Any step in a computation where you can't uniquely tell what the input state was just by looking at the output state where information about the past is lost must, by the laws of thermodynamics, dissipate a minimum amount of energy as heat.
How much energy?
At least kT times the natural logarithm of 2 per bit erased, where k is Boltzmann's constant, T is the absolute temperature. It's tiny for 1 bit, but multiplied by billions of transistors flipping billions of times a second.
So the bottleneck isn't thinking, it's forgetting.
In a fundamental thermodynamic sense, yes. Information isn't just abstract zeros and ones. Manipulating it, and especially discarding it, has a real, unavoidable physical energy cost.
Wow. Okay, so if erasing information costs energy, is there a way to compute without erasing?
That's the idea behind reversible computation.
Yeah.
If you could design your computation so that every single step is logically reversible, meaning you could perfectly reconstruct the inputs just by looking at the outputs then, in principle.
No information is erased.
Exactly. And if no information is erased, then that fundamental KT-ln2 energy cost per step required by Landauer's principle doesn't apply. Theoretically, you could compute with zero thermodynamic energy dissipation for the logical steps themselves.
Are there simple reversible operations?
Sure. The NOT gate is reversible. If the output is 1, the input must have been 0, and vice versa. A more complex building block is the controlled NOT gate, or CCN gate, sometimes called the Fredkin gate. It has 3 inputs and 3 outputs, and the mapping is perfectly reversible.
You can run it backwards.
You can write it backwards. And it's actually universal, meaning you can build any reversible computation using just CCN gates.
Feynman uses a physical model too, right, with potential energy.
Yeah, he describes this theoretical reversible copier using potential energy wells. Imagine a particle representing a bit in a double well potential. You could, in theory, slowly and carefully change the shape of the potential wells, the forces, to gently nudge the particle from one state, copy it to another location's well, and restore the original, all while ensuring the system always has a unique minimum energy state to fall into.
If you do it slowly enough.
If you do it infinitely slowly, in theory, it requires no net energy input. But this highlights the trade-off. Real-world irreversible computation needs energy input, partly to overcome thermal noise, to make sure the switches flip reliably and quickly despite random jiggling.
So faster means more energy needed to be definite.
Generally, yes. You need to push the system harder to overcome randomness and make the transitions happen quickly and reliably. Reversible computing, while theoretically energy efficient per step, might be inherently slow or require incredibly precise control.
Could it be useful, though? Maybe not for speed.
Feynman speculates it might be useful, perhaps in error correction. If you can run parts of a complex computation forward and then backward reversibly, maybe you can spot discrepancies or errors more easily. It's an interesting thought.
And to show it's not purely abstract, he talks about the billiard ball computer.
Right, a concrete, classical mechanical model. Imagine bits represented by the presence or absence of a billiard ball on a path. Logic gates are implemented by carefully angled collisions between balls or reflections off fixed walls, mirrors.
And collisions are reversible in physics.
Perfectly reversible, according to classical mechanics. So you could imagine setting up balls, letting them collide through a series of gates, getting an answer, and then reflecting the output balls perfectly back through the system to recover the original input balls.
But the catch?
The catch is perfection. Any tiny error, a ball slightly off angle, a bit too slow, friction, a bump on the table gets magnified with every collision. To make it work, you'd need an impossibly perfect setup or some way to constantly correct the ball's paths without dissipating energy, which seems incredibly hard. It shows the challenge of fighting noise even in classical reversible systems.
Which kind of leads naturally into the next frontier he explored, quantum computers.
Exactly. Instead of classical bits being 0 or 1, you use quantum systems like an atom's energy levels or a photon's polarization to represent quantum bits or qubits.
And qubits can be 0 and 1 at the same time.
In a sense, yes. They exist in a superposition of states until you measure them. Data is encoded in a collection of these qubits, and computation involves applying carefully controlled physical interactions to make the quantum system evolve over time.
How does this relate to reversibility?
Well, the fundamental equations governing how quantum systems evolve over time, the Schrödinger equation, describe transformations that are mathematically represented by unitary matrices. And unitary transformations are inherently reversible.
So quantum mechanics itself is reversible.
The basic evolution is yes, which means quantum computation is, in its nature, reversible computation. That CCN gate we talked about. It can be implemented as a specific unitary operation acting on 3 qubits.
But building them is hard.
Extremely hard. Quantum states are incredibly delicate. Any interaction with the outside environment, heat, stray electromagnetic fields, even just trying to measure them, can disrupt the fragile superposition and coherence needed for the computation. This decoherence is the major physical obstacle.
And controlling the interactions precisely is tough, too.
Very tough. Feynman discusses the challenges of engineering the specific interactions needed between qubits, especially as you scale up, and exploring simpler schemes, maybe involving only interactions between small groups of qubits at a time, or introducing new primitive elements.
Even getting rid of intermediate results, the garbage has to be done carefully.
Right. Since erasure costs energy, or in quantum terms causes decoherence, you often need reversible ways to handle garbage. A common technique is to copy the final answer, then run the entire computation in reverse to return all the intermediate qubits to their clean initial state. Reversible garbage collection, essentially.
Okay, let's shift back from the far future to the here and now. How are the computers we actually use built? The silicon chips, the VLSI.
Right. Very large-scale integration. The workhorse, the fundamental switch in almost all modern digital electronics, is the MOSFET, metal oxide semiconductor field effect transistor.
Sounds complicated.
The principle is pretty neat, though. Think of it like a tiny electrical faucet. You have a source and a drain where current electrons wants to flow. Between them is a channel. Over the channel, insulated by a thin layer of oxide, is the gate.
And the gate controls the flow.
Exactly. Apply voltage to the gate. This creates an electric field that penetrates the oxide and either allows electrons to flow through the channel, turning the switch on, maybe representing a 1, or blocks the flow, turning it off module. It's a voltage-controlled switch.
And the big physical problem with these in practice is energy and heat, like we said.
That's the main one, especially with the dominant CMOS technology, complementary metal oxide semiconductor. CMOS uses pairs of MOSFETs, one type called NMOS, one PMOS, to make logic gates. Switching a CMOS gate from 0 to 1 or 1 to 0 involves charging or discharging tiny capacitances associated with the gate and the wires.
And charging capacitors costs energy.
It does. Every time you charge a capacitor C through the resistance of the on transistor by applying a voltage V, you dissipate energy, roughly proportional to CV tech. It gets lost as heat.
Billions of transistors, billions of times a second.
Adds up to a lot of heat.
Yeah.
That's why chips need cooling fans or heat sinks. That CV loss is a major limitation.
Feynman looked at ways to maybe reduce that loss.
He explored ideas. One was using inductors in the circuit. Inductors resist changes in current, like electrical inertia. Maybe you could use them to sort of catch and recycle some of the energy when switching, instead of just dissipating it as heat.
Like catching water in another tank instead of letting it spill.
Kind of like that, yeah. Another idea involves carefully controlling the power supply voltages, sometimes called adiabatic charging or hot clocking. The principle is to try and switch the transistor only when the voltage difference across it is very small.
Minimizing the V in CV.
Exactly. If you can charge the capacitor by always keeping the pipe level with the rousing water in the tank, you lose much less energy. It's physically clever, but often complex or slow to implement.
He also had this other concept, dissipated action.
Ah, yes. Energy multiplied by time. He suggested that for a resistive switch like a transistor, the product of the energy dissipated during a switching event and the time it takes to switch might be roughly constant for a given technology.
And making things smaller helps.
Definitely. He noted that shrinking transistors has dramatically reduced this energy time product. It showed excellent scaling behavior, which is a huge reason computers have gotten so much more powerful and efficient over the decades.
How do they even make these billions of tiny transistors on a chip, the VLSI process?
It's an incredible feat of material science and engineering. You start with an ultra-pure wafer of silicon. Then you build up layers, silicon dioxide, an insulator, polysilicon, the conductor, metal layers for wiring. You use masks, like stencils and light, to pattern these layers.
And doping, adding impurities.
Crucial. You selectively introduce tiny amounts of impurity atoms, like phosphorus or boron, into the silicon in specific regions. This changes silicon's electrical properties, creating the N-type and P-type semiconductor regions needed for the source, drain, and channel of the MOSFETs.
So transistors are formed where these different layers and doped regions overlap in just the right way.
Precisely. Where a polysilicon gate line crosses over a doped diffusion path, separated by the thin oxide layer, you get a transistor. It's all defined by the masks used at each layering and doping step.
Building circuits then involves connecting these transistors.
Yes, using the patterned layers of polysilicon metal with connections made through vias or contacts between layers. You build basic gates like inverters, NAND gates, NOR gates, and wire them together to make flip-flops, adders, shift registers, eventually the whole processor.
Wiring itself must become a problem eventually, right? Just physically connecting everything.
Absolutely. It's a huge limitation in VLSI design. As you pack more and more logic gates onto a chip, the sheer amount of wiring needed to connect them grows enormously. Feynman mentions Rent's rule.
What's that?
It's an empirical observation, not a strict law, but it holds up pretty well. It says that the number of external connections, pins or terminals, needed for a block of logic tends to scale with the number of gates inside that block, raised to some power less than 1.
Meaning more gates need disproportionately more connections relative to their count.
Kind of. It means the wiring complexity grows fast. You quickly run into physical limits imposed by the 2D or quasi-3D geometry of the chip. How do you route all those wires without them interfering or taking up too much space? It constrains chip density and architecture.
Wow. So, okay, we've taken quite a journey here. From Feynman's view of computers as fundamentally physical machines,
Through the abstract limits of what's even computable with Turing machines.
down to the very real physics of error correction with Hamming codes. The thermodynamic cost of erasing information?
The weirdness of quantum computing, and finally, the nuts and bolts of how we actually build today's silicon chips with transistors and wires.
And seeing it through this physical lens, like Feynman encourages, really shows you that the limits we hit aren't just about clever algorithms or math. They're baked into the universe.
Exactly. Thermodynamics, quantum mechanics, even just plain geometry. These physical laws set fundamental boundaries on what computers can do, how fast they can do it, and how much energy it takes.
And understanding this isn't just, an academic exercise for you listening. It explains so much about the technology you use every single day. Why your phone battery drains, why laptops need fans, how data gets compressed, how systems manage to be reliable at all.
And it points towards where things might go next. If we want fundamentally more powerful or more efficient computation, we might need to harness different physics, like quantum mechanics or master reversible computing.
Which leaves us with this final thought to chew on, building on Feynman's ideas. He speculated about that dissipated action, the energy, time for a switch maybe being some kind of fundamental constant, perhaps even linked to quantum uncertainty.
Yeah, like maybe there's a minimum energy times time cost related to Planck's constant for any information processing step at the most fundamental level.
So the question is, if that's true, if there is such a deep physical cost tying energy and time together for computation, what does that really imply? What kind of truly revolutionary physics or engineering would we need to somehow get below that limit, if it even exists? That's something to ponder.